So till the last lecture we had seen the types of differential equations. We started with the variable separable, the homogeneous differential equation, the exact differential equation, and then the reducible to exact. Today we will go ahead with the fifth type of differential equation called as the linear differential equation. So it is type number 5, which is linear differential equation, which simply means that the order of this differential equation is always going to be 1. It will be in the form, there are 3 different forms of it. The first one is dy by dx plus p into y is equal to q, where p and q are functions of x. Now if this differential equation is to be solved, then we will be requiring the integrating factor for it, and that integrating factor is directly defined as integrating factor is equal to e raised to integral p dx. Now of course, to solve this entire thing, we will have to proceed with our usual discussion of considering the equation to be exact or reducible to exact. For the time being, we can remember the formula as integrating factor is e raised to integral p dx, and then the solution of this differential equation will be if, that is integrating factor, into y equal to integral if into q dx plus c. This is going to be the solution of linear differential equation in form 1. Of course, though the proof is not expected, we will just have a look at how this particular integration factor has been found out. The given equation was in the form dy by dx plus py is equal to q. Therefore, it can be written as dy by dx is equal to q minus py, and if we cross multiply, we will get it as dy equal to q minus py into dx. Rewriting the equation, we will get it as q minus py into dx minus dy equal to 0. Thus in this case, comparing this equation with our form for exact, that is m dx plus n dy equal to 0, we get m is equal to q minus py, whereas n comes out to be minus 1. So dabba m by dabba y comes out to be, as you are differentiating with respect to y, differentiation of q will be 0 minus p. So dabba m by dabba y comes out to be minus p, whereas dabba n by dabba x will be straight away 0. So we say that the equation is not exact because dabba m by dabba y is not equal to dabba n by dabba x. So we will have to check whether it is reducible to exact, and for reducible to exact we have got a formula where we can start with m, divide by n, and it should be function of x. That was the third type which was available. So we just test what is dabba m by dabba y minus dabba n by dabba x upon n. It comes out to be minus p minus 0 upon minus 1, which is equal to p, which is nothing but function of x. And over there we have said, with reference to reducible to exact, integrating factor will be e raised to integral fx dx, and so in this case it comes out to be e raised to integral p dx. Let us just repeat the process that we have over here. The differential equation was in the form dy by dx plus py equal to q, where p and q were functions of x. We have directly written integrating factor as e raised to integral p dx and the solution as if into y equal to integral if into q dx plus c. But we are required to prove it, though it is not in the course of the syllabus as such. We'll start with the given differential equation as dy by dx plus py equal to q, and we will rewrite it in the form which is comparable with exact. So we get it as q minus py into dx minus dy equal to 0. So m comes out to be q minus py and n is minus 1. Dabba m by dabba y, that is, we are required to differentiate m with respect to y treating x as constant. Q being function of x, its differentiation is 0, and py will be differentiated with respect to y, will come out to be p. So dabba m by dabba y is minus 1, whereas n being minus 1, its differentiation will be straight away 0, and we find that dabba m by dabba y is not equal to dabba n by dabba x. So the equation is not the exact one. So we have tested for reducible to exact form, and we have put the test as dabba m by dabba y minus dabba n by dabba x upon n, which comes out to be minus p minus 0 upon minus 1, which is p, which is nothing but function of x. And through reducible to exact, we got the integrating factor as e raised to integral p dx. Now the solution. We said that the given equation should be multiplied by the integrating factor. Now if I multiply this equation by the integrating factor, then I will get it as if into bracket q minus py dx minus if into y equal to 0. So this whole thing will become my m, and minus if will be n. The solution that we were talking of over there was to integrate m with respect to x, treating y as constant. So it will be if into bracket q minus py dx. So integration of m with respect to x treating y as constant, and from n only those terms which do not contain x, and from n only those terms means we don't have even a single term over here, it will be equal to constant. So if we separate out, we will get if into q dx, and then it will be minus y is constant, it will be integral if into p dx equal to constant. Now in this case, this becomes the right hand side, that is if into q dx plus c, and on the left hand side we can integrate this if, because this if is nothing but e raised to integral p dx. So integral if into p dx can also be integrated by substitution, and that answer will simply come out to be e raised to integral p dx, because differentiation of integral p dx is nothing but p dx. So it will be in the form that e raised to fx into f dash x dx will be the format for the integration of it. So this comes out to be e raised to fx into f dash x, and this integration will simply come out to be e raised to fx, which is nothing but e raised to integral p dx, that is if, and so this becomes minus y into if equal to constant, and we have got the solution in the form if into y equal to integral if into q dx plus constant. For us, even if we remember only the formula for integrating factor and the formula for the solution, that should be more than sufficient. Nobody will be asking us to prove the result. That was form number 1 in the linear differential equations. The second form that we have is known as the Bernoulli's form. So form number 2 is Bernoulli's form, which says that it is in the form dy by dx plus py equal to q y raised to n. Now if the differential equation is in this form, where p and q are again functions of x only, then to solve it we are required to get it back in the first form. For this purpose we are required to have some derivation, that is dy by dx plus py equal to q y raised to n. We say that divide by y raised to n, and we get it as y raised to minus n dy by dx plus p into y raised to 1 minus n is equal to q. So once we divide by y raised to n, and then if we check, if y raised to 1 minus n is assumed to be z, because we have already managed the right hand side, this should be in the form of py, referring back to our form number 1. The right hand side must be a function of x, which we have managed now, and the left hand side, first term should be dy by dx and second term should be p into y. So I am trying to manage p into y raised to 1 minus n as p into z, and if I differentiate this with respect to x, we will get it as 1 minus n into y raised to 1 minus n minus 1 dy by dx equal to dz by dx. So this 1 cancels and we get it as 1 minus n y raised to minus n dy by dx equal to dz by dx. So this appears to be a simple way of conversion, because 1 minus n as it is a constant entity. So to this equation, if we multiply by 1 minus n, we get it as 1 minus n into y raised to minus n dy by dx plus 1 minus n into p into y raised to 1 minus n equal to 1 minus n into q, and then substitute for y raised to 1 minus n as z. We get it as dz by dx plus 1 minus n into pz is equal to 1 minus n into q. Now this form is not matching with the given form, but we can temporarily say that 1 minus n into p will be simply function of x only. Let us call it as, say, p1, and similarly 1 minus n into q will be again a function of x only, say p2, or we can say it as q1, and then this form reduces to, this form will reduce to dz by dx plus p1z equal to q1, where p1 is nothing but 1 minus n into p, q1 will be 1 minus n into q, and z is nothing but y raised to 1 minus n. we have the equation which is linear in z and x. So if it is linear in z and x, then we can always use the previous formula. Here we can use the previous formula by replacing y by z, and integrating factor will be, in this case, e raised to integral p1 dx. The formula will turn out to be if into z equal to integral if into q dx plus constant. Rather, q ke bajaye it will be q1. And so we say here that now the equation is linear in terms of z and x. Solve it by method number 1, same formula, but remember, in this case, do not forget to resubstitute z as y raised to 1 minus n, because the answer must be in terms of x and y. This is the important note that you will have to follow. The equation can be very well reduced to the first form, and it will be a simple and a straightforward task. So up till now we have seen two forms of the linear differential equation. Form number 1, that was dy by dx plus py equal to q, and form number 2, which is Bernoulli's form, that is dy by dx plus py equal to q y raised to n. There is one more form, form number 3, which is written as form number 3. It is f dash y dy by dx plus p into fy equal to q, where p and q are again functions of x. This problem is much simpler because we can straight away say that let f of y be is equal to z. Therefore, f dash y dy by dx will come out to be dz by dx, and if we simply substitute, we get it as dz by dx plus pz is equal to q, which is again reducing to form number 1 that we have, which is linear in z and x. Carrying the same note again, do not forget to resubstitute z as f of y. This note is also very important, and these are the three forms of linear differential equations which we are required to study. And after checking form number 1, form number 2, form number 3 of the form number 3 as well as 4, that is variable separable, that was our first way of solving the differential equation, variable separable. Second was homogeneous. Third was exact. Fourth was reducible to exact. And now we have studied the fifth one, called as linear differential equations. Remember these formulae, because we had variable separable as a unique method, adjustment, homogeneous is observation, variable separable is adjustment type of method, homogeneous is through the observation, exact is condition based. whereas reducible to exact was in a way trial. We had 5 or 6 different formulae into it. Linear is again a trial. It has got 3 different forms. And then we also have something called as a method of substitution, which we will be studying afterwards. Let us now go further for the problems which are related to linear differential equations. We have been learning these differential equations. So far as these problems are concerned, as we consider the method and the problems based on it, at that time it is going to be a very simple and straightforward task, because we are quite aware of the fact that the equations or the problems which are given to us, they belong to a particular type of method. Even this particular set that I am going to give you, this set you are quite aware that it is going to be the linear differential equation only, and will be any one of these 3 forms which we have studied up till now. But afterwards, once we complete even the 6th method, then the problem will be one of the severe ones, because every time you look at the differential equation, probably you will think of solving it either by exact or reducible to exact or linear or substitution, and you cannot just go for applying all these methods one after the other. Of course, with that you will definitely get the solution, but you need a larger amount of efforts in this direction to adjust the terms and to view the equation in the proper form. It may not be given in that particular form every time. Like for example, the given set of differential equations. Observe that the first equation, x dy by dx plus 3y equal to x raised to 4 e raised to x raised to minus 2 y cube. We are definitely aware of the fact that you cannot separate out the variables, because you don't have power of y which cannot be taken as common, and y cannot be separated out. We can think of homogeneous, because of e raised to term it cannot be homogeneous. Exact could be one trial, otherwise reducible to exact, but the form is directly in the method, like dy by dx plus py is equal to q y raised to n is going to belong to the linear differential equation, because the dy by dx term is also there. If you observe the second differential equation, then it is a totally different form. It appears to be m dx plus n dy. So we will be always coming through the check of exact differential equation. Third one is again x dy minus y into bracket so many terms over here, and we cannot exactly make out whether it is going to be a linear when it is given in the mixed form. Whereas this particular equation over here, equation number 4, it is directly in the form y cube's derivative 3y square is available. It is going to be f dash y dy by dx plus p into fy equal to q, a direct form for linear equation. Similarly over here, again it will be 3y square will form derivative of y cube and is again a linear differential equation. Here we will have to test, we are not sure, there is a term of y raised to half on the right hand side that should be brought back to the left hand side. And even the 7th equation, at the first look you cannot decide whether it is going to be a linear one. But now that we are in the 5th technique of solving the differential equation, it is bound to be all these cases, all these problems are solvable through the linear form only. Let us solve the first problem. It is x dy by dx plus 3y is equal to x raised to 4 e raised to x raised to minus 2 y cube. That is our form number 2, called as the Bernoulli's form. The Bernoulli's form says that we are required to throughout divide by y raised to n. So we say here divide by y raised to 3, and therefore we get it as y raised to minus 3 into x dy by dx. Of course we don't want this x, so we can very well say that divide by y raised to 3 into x. So from here x will vanish and y raised to minus 3 term will come into picture, plus it is 3y upon xy cube equal to x raised to 4 e raised to x raised to minus 2 y cube upon xy cube. So we get it in the form y raised to minus 3 dy by dx plus 3 upon x y raised to minus 2 equal to x cube e raised to x raised to minus 2. Substitution, we were aware of the fact that this should be something like z, so we will say let y raised to minus 2 is equal to z, therefore minus 2 y raised to minus 3 dy by dx will turn out to be dz by dx. So we will multiply the given equation first of all by minus 2 and then we will substitute. So it will be minus 2 y raised to minus 3 dy by dx minus 6 upon x y raised to minus 2 equal to minus 2 x cube e raised to x raised to minus 2. And then we substitute y raised to minus 2 as z, and so the first term will turn out to be dz by dx, second term is minus 6 upon x as it is into z equal to minus 2 x cube e raised to x raised to minus 2. So this is going to be our term p, and this entire thing is q. So we have brought the equation in form number 1. Integrating factor for this particular equation by the method, by the formula, is e raised to integral p dx. The form that we have got was dy by dx minus 6 upon x z, rather it is dz by dx minus 6 upon x z equal to minus 2 x cube e raised to x raised to minus 2. And so as we substitute p, it will be e raised to integral minus 6 upon x dx, which is e raised to minus 6 log x, which will turn out to be x raised to minus 6 as the integrating factor. The solution by formula 1 is if into z equal to integral if into q dx plus c. So it will be x raised to minus 6 into z equal to integral if is x raised to minus 6, q is minus 2 x cube e raised to x raised to minus 2 dx plus constant. So to integrate right hand side, we will first multiply by x raised to minus 6 to x cube, and we will get it as x raised to minus 3 e raised to x raised to minus 2 dx plus constant. Substitution will be let x raised to minus 2 is equal to t, therefore minus 2 x raised to minus 3 dx will be dt. And so we already have this term minus 2 x raised to minus 3 and dx, which can be substituted as dt, and this will simply turn out to be integral e raised to t into dt plus constant. So it comes out to be e raised to t as the solution of integral plus constant of integration. T is to be resubstituted, it is e raised to x raised to minus 2 plus constant. And so the solution will appear to be x raised to minus 6 into z equal to e raised to x raised to minus 2 plus constant. We have already said that we should not be forgetting to substitute for z. So the solution that we are getting right now should be rewritten first of all. So the solution is x raised to minus 6 into z equal to e raised to x raised to minus 2 plus constant, and z is to be substituted. If you look back, it is going to be y raised to minus 2, which we have substituted, is e raised to x raised to minus 2 plus constant, can be written as 1 upon x raised to 6 into y square equal to e raised to x raised to minus 2 plus constant as the solution for problem number 1. So the procedure is not at all a difficult one. We will have to simply get the equation in the appropriate form, and the problem is very well solvable. Nature of the equation will itself suggest as which of the three forms for the linear is to be used. Linear equation must always contain a term like dy by dx, without which we cannot proceed. As we see problem number 2, where we do not have a mention of the term dy by dx, which we will have to first of all bring in the equation, that is by dividing throughout using dx. So problem number 2, which is 1 plus x square dy equal to tan inverse x minus y dx, is to be rewritten first of all as 1 plus x square dy by dx equal to tan inverse x minus y. Our form is dy by dx plus py equal to q. We don't want any multiplier for dy by dx, so we will be dividing throughout by 1 plus x square, giving me dy by dx equal to tan inverse x upon 1 plus x square minus y upon 1 plus x square. This term should be taken to the left hand side to match with the form. So it will be dy by dx plus 1 upon 1 plus x square into y equal to tan inverse x upon 1 plus x square. Now it is a perfect match with the given form. This will be p and this is going to be q. It is form number 1 only. P and q should be functions of x, and so integrating factor by the formula will come out to be e raised to integral p dx, that is 1 upon 1 plus x square dx. Integration of 1 upon 1 plus x square is tan inverse x, so integrating factor comes out to be e raised to tan inverse x. Solution by the formula is if into y equal to integral if into q dx plus constant. So it will be e raised to tan inverse x into y equal to integral e raised to tan inverse x into q is tan inverse x upon 1 plus x square dx plus constant. So we are simply using the formula for the solution and substituting value of integrating factor. And so what we have right now, I am just rewriting the step. It is e raised to tan inverse x into y is equal to integral e raised to tan inverse x into tan inverse x upon 1 plus x square dx plus constant. Substitution is suggested by the nature, so we will have to substitute for tan inverse x. So we will say let tan inverse x is equal to t. Therefore 1 upon 1 plus x square into dx will be dt. Substituting in the right hand side, we get it as integral e raised to t. See, this dx upon 1 plus x square is going to form dt. So tan inverse t will remain as t into dt plus constant. As there is a product, we will have to integrate it by parts, taking t as function 1 and e raised to t as function 2. So it will be retained first into integration of e raised to t is e raised to t minus integral differentiation of first is 1, integration of second e raised to t is e raised to t dt plus constant. So this comes out to be t into e raised to t, integration of e raised to t is again e raised to t plus constant. This can very well be remembered as a formula. It is t minus 1 e raised to t plus constant. A formula that is e raised to t into t, when is integrated you will get it as t minus 1 e raised to t. And now we will have to resubstitute. Resubstituting, we get the solution as e raised to tan inverse x into y equal to into bracket tan inverse x minus 1 into e raised to tan inverse x plus constant. That is the solution of problem number 2. Though the terms involved in the problem were complicated, like tan inverse x, 1 plus x square, still the problem turned out to be one of the simplest problem because it was directly available as the linear differential equation. You can have a look at the problem. We have simply adjusted the term 1 plus x square by which we have divided, and we simply matched it with the form, that is dy by dx plus py equal to q. P was integrable, so we got integrating factor as rather a complicated one, e raised to tan inverse x, but that has to match with the right hand side because the integration was also simple and straightforward, and that's why IF turned out to be a complicated one. Let us proceed to the third problem. Problem number 3. As we read it, it is x dy minus into bracket y plus xy cube into bracket one plus log x dx equal to 0. We know that it is linear, so the procedure will be simple. You will have to first of all get dy by dx, so it will be x dy by dx minus y plus xy cube into bracket 1 plus log x equal to 0. And we don't want any multiplier for dy by dx, definitely not function of x. So we divide by x to get the form as dy by dx minus y upon x plus y cube into bracket 1 plus log x equal to 0. Rewriting to match with the form, it is dy by dx minus 1 upon x into y equal to minus 1 plus log x into y cube. And observe that it is in the form dy by dx plus py equal to q y raised to n. that is Bernoulli's form. For this we will have to divide by y cube, and we will get it in the form minus 3 y raised to minus 3 dy by dx minus 1 upon x y raised to minus 2 equal to minus of 1 plus log x. We know that y raised to minus 2 is to be substituted as z, and it will be minus 2 y raised to minus 3 dy by dx will become dz by dx. So let us multiply, because the same substitution we have done in the one problem before it. So multiply by minus 2, we get it as minus 2 y raised to minus 3 dy by dx plus 2 upon x y raised to minus 2 equal to 2 into bracket 1 plus log x. And now if we substitute, let y raised to minus 2 equal to z, therefore minus 2 y raised to minus 3 dy by dx equal to dz by dx. Bernoulli's form has got always the substitution as y raised to 1 minus n is equal to z. As we substitute, we get the equation as dz by dx plus 2 upon x into z is equal to 2 into bracket 1 plus log x. So this is going to be our new P, P1. This is new Q, Q1. The solution is IF. Oh, before that we are required to find IF. Integrating factor now is e raised to integral P1 dx, not the original P, this is a modified one. So it will be e raised to integral 2 upon x dx, which is e raised to 2 log x, which is nothing but e raised to log of x square, that is x square. And so the solution will be IF into z equal to integral IF into q dx plus c. So it will be x square z equal to integral x square into 2 into bracket 1 plus log x dx plus constant. As log term is definitely not integrable, I will take this 1 plus log x as function 1 and x square as function 2, and will proceed for integration by parts. We are required to perform integration by parts because of the product which is appearing inside the integral, and secondly, being the log term involved, we will proceed with that term as function 1. And so we have x square z equal to twice integral 1 plus log x into x square dx plus constant. Retain first, that is 1 plus log x. Integrate second, integration of x square is x cube by 3. Minus integral, differentiate first, 1 is differentiated as 0, log x is differentiated as 1 upon x. Integration of second, that is x cube by 3 dx plus constant. So this will be 2 by 3 x cube into 1 plus log x, first term. Second term will be minus 2 by 3 integral, observe that this x will cancel, it will be again integral x square dx plus constant. It comes out to be 2 upon 3 x cube into bracket 1 plus log x minus 2 by 3 into x cube by 3 plus constant. If you want, you can simplify, because x cube term can now be taken common. it is x cube into bracket 2 by 3 minus 2 by 9, and the second term that remains is plus 2x cube log x upon 3 plus constant, left hand side being x square z. Simplification which could be possible is simply to take the LCM, that is multiply by 3, it will be 6 minus 2 4, it will be 4x cube by 9 plus 2x cube log x upon 3 plus constant, and the z that we have substituted, we should substitute over here, was y raised to minus 2. Solution can be kept in this form. If you want, you can multiply throughout by y square as well as 9. So if you multiply by 9y square, then you will get it as 9x square is equal to, 9 will cancel from here, it will be 4x cube y square, and 3 will cancel, it will be 2 into 3, it will become 6x cube y square log x plus constant. Of course, the solution, once you eliminate the differential coefficient, you can keep it as it is at any stage. So even this is a valid solution, this is valid, this is not the valid one because of the presence of z, because you are solving the differential equation in x and y. Simple one became lengthy because of the numerical calculations and simplification. Integration by parts was again not at all a difficult one. Because of the log term, we can easily decide as which one should be function 1. So the third problem is through. Let us proceed to the fourth one. And the fourth problem is given as 3y square dy by dx plus 2x y cube equal to 4x e raised to minus x square. It was directly in the form f dash y dy by dx plus p into fy equal to q. That was the third form which was available. And so the substitution is also simple. We can say that let y cube is equal to z. Therefore, 3y square dy by dx will be dz by dx, and it will turn out to be dz by dx plus 2xz is equal to 4x e raised to minus x square, 2x being p and 4x e raised to minus x square will be q. If is e raised to integral p dx, which is e raised to integral 2x dx, will turn out to be e raised to x, or rather 2 into x square by 2, which is e raised to x square. Solution is if into z equal to integral if into q dx plus constant. So it will be e raised to x square into z equal to integral e raised to x square, q is 4x e raised to minus x square dx plus constant. Of course, these two will cancel each other. As the powers get added, it will be e raised to 0 will be 1. And so we are required to simply integrate 4 times integral x dx plus constant. So it is 4 into x square by 2 plus constant, which is 2x square. And we will resubstitute z, which was y cube. So it will be e raised to x square into y cube is equal to 2x square